Now, oddly enough, I am not going to start with the idea that integration is the reverse of differentiation. I'm going to start from a different perspective, okay? So here's the idea, and I'm going to give you 5 minutes to work this out, okay? I'm going to draw a graph on the screen, or on the board, okay? So I'm going to draw the graph y equals x squared minus 6x plus 13, okay? So it's going to look something like this, okay? So it's going to be 3, that's going to be 4, okay? So it's the graph y equals x squared minus 6x plus 13. What I want you to do is I want you to work out the area underneath this graph between -1, okay, -1 and 2. Boys, -1 and 2. So I want you to find the area underneath this graph. So by the area underneath this graph, I mean the area between the x-axis and this graph, between -1 and 2, okay? I am going to give you, so if you know about integration, don't spoil it, okay? I'm going to give you 3 minutes to have a go at this, okay? Just think about a strategy which you could use to find the area underneath this graph. Appreciate it's a bit wonky, but it'll do. Okay, so let's have a think about this then, okay? So all I want you to do is think about how we could find the area underneath y equals x squared minus 6x plus 13 between -1 and 2. Any suggestions? Okay, so you could kind of square this off. Because remember, I just said find the area, I just said approximate the area, okay? So why not break this shape up, why not break this area up into areas that we do know how to find, okay? Why not rectangles? Rectangles would work, wouldn't they? Okay, so let's go for a rectangle. Let's round this one off. Okay, so we've got that rectangle there, and then we could maybe break up the rectangle between, I don't know, 0 and -1, then maybe another rectangle between 1 and 2. Why not? Okay, so I've got 3 rectangles now. Because I know how to work out the area of a rectangle. What is it? How to work out the area of the rectangle?
X multiplied by y.
That multiplied by that. Yeah, exactly. So in other words, that distance there is just going to be some change in the x direction. You happy? That's my x direction. It's just some change in the x direction. Okay? And the height of the rectangle is given by what? That thing, isn't it?
Yeah.
Okay, when I stick my x value into there. Okay, so the height of the rectangle is just going to be given by my y value when I stick it, so my x value when I stick it into this function, my y value. Okay? So in other words, my area of this particular rectangle is just going to be y multiplied by some change in x. Okay? Right. Okay. Would you be happy then to find the area of the shaded region as best I possibly can? I'm going to add together all of these rectangles together. Okay? So to find the area which I'm after, so the area of the region, okay, I'm going to add together all of these rectangles together. So I'm going to take y and multiply it by dx for each of these individual ones, okay? And I'm just going to add them all together. Well, a better way of saying add together is by writing that symbol there, which means what? You've seen that before in probability. What does that mean? Sum, exactly. Add them together. Okay, and I'm going to start at -1, okay? And I'm going to keep going all the way through until I get to 2, okay? So I'm going to start at -1 and go all the way through to 2. So let's try this. Let's try this, okay? For this first rectangle, what is my height? What's my height from here to here?
How do you decide the height? Why? Is it not like higher or lower?
Okay, so my height I'm going to get by sticking -1 into this function. Because can you see the height is just going to be from wherever it starts on the x-axis, 0, up until where it hits the curve. Okay? So if I stick -1 in here, what do I get?
7? No. 8. -2.
Not what I got.
No, wait.
Sticking -1 in here,
Oh, no.
-1 squared is 1. Minus 6 times -1 is effectively adding 6. You end up with 7 from those two things. Add 13. 20. Great. Excellent. Okay, so we get 20 from there. So in other words, the first rectangle is going to be the base, the change in x, which in this case is 1, multiplied by that y value. Okay, so I'm going to get 20 multiplied by 1, which of course is just 20. Do you get the idea?
Yeah.
All right, so for the next one, what's that height going to be? So I'm going to stick 0 into this function. It's going to be 13, right? It's going to be 13. Sorry, that was meant to be 13 there, okay? So that's going to be 13, in which case that area there is going to be 13 multiplied by the same change in x, which is 1. So that gives me 13. Does that make sense? Right? Okay, and then finally, we need to work this bit out. We need to work this bit out here, okay? So what's my height going to be?
8.
Yeah, it's going to be 8, because I'm just going to stick 1 in there, right? So 1 take away 6 is 5. Yeah, add negative 5, add 13, that's going to be 8. Okay, so that area there is going to be 8 times 1, which is equal to 8. Okay? Then if I want approximation for the area then, I can say that the true area is going to be approximately equal to just the sum of all these things. 20 plus 13 plus 8. What do I get?
41.
Yep, that looks about right to me. Why do I write 20 down? 41. Okay, so that's what I'm proposing my area is going to be. Now, here's my question. How could I, this is just an approximation, right? Is it an overestimate or an underestimate? Why is it an overestimate?
Because they are more space.
Exactly. I've also included all of this extra space, which I didn't want. Okay? So because I've included all of that extra space, it's an overestimate. So what can I do to make this estimate better?
Reduce those extra areas.
Good. So how could I do that?
I don't know.
Well, have a think. At the moment, I'm just saying each rectangle is going to have a width of 1. What if I changed it so that the rectangle was a width of
0.
really small? Yeah? If I made it even smaller, would you be happy that then the height of the rectangle would be pretty much the same as the area underneath that curve? Yeah, pretty much match it. So what I'm trying to say then is that I'm going to try and change this so that the area underneath the curve, so that's my area which I want to work out, if I change it so that each rectangle has infinitesimal width. So in other words, it's basically just a straight line. Okay? So each rectangle, I'm drawing rectangles here, even though they're really, really small. Each rectangle has infinitesimal width, really, really small. Okay? So therefore, if I add together all of those rectangles, I would get the exact area. Okay? So if I change this, okay, I'm still going to have y. I'm not going to multiply it by delta x anymore because I want to represent that delta x is really, really small. Exactly the same thing we did with our gradient. Yeah? So if this delta x is really small, what do I change this to?
0.
So it's not delta anymore, it must be... Remember, delta means a big change. Small little delta means a small change. The change which I'm talking about is so small that it's basically 0. So I say d. So that's infinitesimal change. Okay, so I'm talking about infinitesimal change which is so small, it's basically 0. The width of the rectangle is basically just a straight line. It's really, really small. So therefore, I'm going to change this delta to a d. Okay? And to illustrate the point that I'm adding together loads and loads of rectangles of infinitesimal width, I'm going to change this sum. Okay, so sum would be big. I guess an s would be small. I'm going to use an elongated s to represent infinitesimal. Okay? So it's now an elongated s, okay, and the same limits, -1 to 2. Right? Has anybody seen this notation before? If you've looked at integration, you've seen this before. It's literally exactly the same idea as that. It's just you're talking about it in the limiting case. In other words, in the case where the width of the rectangle is so small, it's basically 0. Is that okay? Mm-hmm. Good, fantastic.